Hi everyone, welcome to the YouTube presentation for Group 3 of the final project in data mining. This is Nufra and I'm here with my teammates Rafia Bushra and Tate Smith. We're predicting strokes based on sociological and clinical information. Roughly going over the outline, we have divided our presentation into three main sections. Firstly, we'll talk about the motivation behind our work in introduction and some related works. Then we'll discuss our proposed work at length, where we talk about data processing and the steps we took, and the three different machine learning models we used to build our product. And then we'll discuss the graphical user interface and the application demo. Finally, we'll conclude our presentation with some remarks about the future work and what we have done so far. Stroke is a medical emergency that requires immediate attention, which can lead to death and which can lead to long-term disabilities and even death. It is a highly occurring disease and the third leading cause of death. It's also very unpredictable, even with the advancement of medical technology. Healthcare is the cornerstone of our modern world, and it is rapidly being digitalized. 30% of the world's data is generated by this industry. Since strokes are very hard to predict, mining patterns with data mining algorithms in stroke data can help us in the early detection of strokes, potentially saving lives by taking preventative measures. There have been several papers that uses machine learning algorithms to predict strokes. For example, Considub et al. Suggested a model for predicting strokes based on demographic information that they collected for 3 years, which they eventually narrowed down to 6 primary features risk factors, by analyzing the stroke risk factors and consulting specialists. The paper Stroke Predicting Using SVM uses a regression-based approach to identify the connection between factors and the corresponding impact on stroke to understand the possibility of having a stroke. Look et al. Did a comprehensive study on strokes based from China. Look et al. Does a comprehensive study on stroke with age as their primary focus from people with people from China. For data features, we have 12 features, for the first one being the ID, which we do not need for data processing, and the last one being the target variable, whether someone has stroke or not. The 10 features that we have, we'll use it to predict, we use it as attributes to predict the machine learning models. There are categorical and binary and continuous variables. And
Okay, I'm Tate. I'll be talking a little about the data pre-processing we did before we applied any of our actual algorithms to our stroke data. So when we first got the data set, there were a number of issues with it where we couldn't just feed it straight into our algorithms and get a result. For one, we had missing data in some of our columns. We had a number of different data types. It wasn't just uniform numerical data that we could work with. And then also the scale of the data was very different. Some of the data was scaled between 1 and 1,000, and some of it was just a 1 or 0 binary. So we needed to do some normalization. So a little more specifics on the missing data. Really what we had there was a small number of missing rows in the BMI and the smoking column. What we did was we filled these rows with the mean of the columns. And although this isn't the ideal way to fill missing data sometimes, this was a fairly small number of rows that actually had missing data. It was less than 0.2% of all our rows had this missing data. So we don't expect it would affect our results very much, um, no matter how we filled in the data. But filling in with the mean of the column should be a fairly reasonable thing to do for a small amount of data. In terms of the data types, what we had beginning was Numerical data, we had some columns that were numerical data. There were integers or floats. We didn't need to change that. Although we had some columns that were binary categories, but they were represented as strings, like yes or no, or I think that's all we had in terms of the binary categories is some columns were labeled yes or no. And so we just changed that to an integer representation of 0 or 1 so that we could work with it more easily. We also had some other categorical attributes which were had more than two categories. So like, for example, smoking status had currently smokes, never smoked, or smoked in the past. Um, so we changed that to a one hot encoding. So we would have a column for smokes, where every row that had that categorization smoked, we just made a new column with smokes and put a 1 in that row. In every instance that the person didn't smoke, that had a 0. And so we ended up with three new columns, a column for smokes, a column for never smoked, and a column for smoked in the past. In terms of normalization, we all we did was we scaled the data between 0 and 1 so that one column that was a much larger scale wouldn't end up dominating the prediction. All right, next slide.
The first machine learning algorithm we used for our model is naive Bayes classifier, which is a machine learning algorithm based on the Bayes theorem. It is a system where we update our prior belief based on new evidence. Bayes' theorem states that some some hypothesis, for example, having stroke, is true given an event has occurred. Let's say losing the basic muscle movement, and it's calculated by the prior probability of having a stroke multiplied by the likelihood that you would lose the basic muscle movement if you had a stroke divided by the total probability. The goal is to determine the most likely class given all the attributes, that is, to maximize the posterior probability. Um, we do that by calculating the likelihood times the prior probability. So the likelihood is calculated the by calculating all the likelihood is calculated by finding the probability of all the features given a class times the probability of that class. And this has to be done for every single class in our data set. In this case, stroke or no stroke. The probability of the features can be broken up and calculated individually because naive Bayes assumes features to be independent of one another. Next slide. For implementing naive Bayes, we had to do a little bit of pre-processing, which is label encoding the categorical values and choosing features with only low correlations, as it is assumed that the features are independent of one another. For training our model, we figured out the mean and standard deviation of every features for every class. For example, the mean and standard deviation of all the 10 features for class stroke and for class no stroke. And then we had to calculate the prior probability, which is just the number of times an instance has occurred divided by the total number of divided by the total observations. We used Gaussian density functions to predict the likelihood, to calculate the likelihood, and then we used the likelihood and prior probability to calculate the posterior probability, and we chose the highest class probability for predicting our class. Next slide.
This is Rafia Bushra. I did the decision tree classifier algorithm for our project. Decision tree is one of the most widely used classification algorithm used in predictive modeling. We used a variation of Hunt's algorithm where we do use a greedy approach, which means that during splitting a node, we pick the split that gives us, that minimizes the impurity going from a parent node to a child node. We only allow binary splitting, like a variation of the Hunt's algorithm, like CART. We handle the missing values before we start splitting, and splitting attribute is determined at every single node. The most important aspects of this classifier are deciding what the splitting criterion should be, like which impurity measure should we use to choose what attribute we split based on. The stopping criterion, which is the termination condition, which tells us which node becomes a leaf node, where we won't divide that node any further. How we handle our missing values, the attributes we choose. For example, as Nusra mentioned earlier in data processing, that we don't use the ID column as it doesn't have any impact on decision making. And then the data pre-processing, which is quite different from what Tate discussed which is quite different from what Tate discussed in general, as it requires a different kind of pre-processing for decision tree. For the splitting criterion, we chose to do entropy measure, which gives us information gain. This is similar to C4.5 method. For entropy, entropy is measured using the equation shown here. Here, PIT is the fraction of instances belonging to a class T, belonging to a class I in node T. And C is the total number of class labels, which in our case is 2, since a person either is susceptible to stroke or is not. So so this is how we calculate entropy at a particular node. Information gain is defined as the difference in entropy before and after a node is split. A parent node is the node that we had before splitting, and child nodes are the nodes we get after splitting. The entropy of child, or here as shown here, is the weighted sum of all the children nodes. The entropy child I is calculating using this function here, and then we take a weighted sum of the child nodes, and that gives us entropy child. Entropy parent is simply calculated using this function here. And this gives us information gain. And at every single node, we calculate the information gain for every attribute, and we find the minimum information gain. Sorry, we find the maximum information gain, which tells us that it minimizes impurity, and we choose that attribute for that particular node. So for stopping criterion, it's an either or between two different stopping criterions. If at a node we have run out of attributes to split based on, or if all the instances in a node have the same class label, then we consider that to be a leaf node. And finally, missing values are handled before splitting starts. We have 2 attributes that has missing values, the BMI attribute, which is a continuous variable. And so we use the mean of the entire column, and we use that to impute missing values. And for smoking status, which is a categorical variable, has 3 different values. We use the mode. Of the 3 values, never smoked, formerly smoked, and currently smokes, we saw that never smoked far outnumbers the other 2 and can be considered the mode of this attribute, and that's what we use to impute. And then finally, one of the most important data processing steps for this algorithm is data binarizing, which is a process of transforming data features into binary numbers so that the classifier algorithm is more efficient. And it helps with binary splitting in this case. We have 10 attributes, 4 of which are already in binary form: hypertension, heart disease, ever married, and residence type. These 4 were already binary attributes, so we didn't have to do anything to them. Gender, we had 3, which is a categorical attribute, had 3 different categories: male, female, and other. We see that the other category has so 11 instances out of 43,400 records, which is very insignificant, and we don't have enough information on this category. So to make the algorithm more efficient, we drop these 11 instances and work with the rest. Smoking status has 3 different categories, and we can't drop any of them since they do have significant information about those all 3 categories. However, never smoked and the other 2 has a meaningful distinction. Never smoked are people who has never smoked in their life, and formerly smoked and smoked categories are people who has smoked at some point. So it's smoker versus non-smoker. So we group these 2 together, and we have a binary value here. Either they smoked or they didn't. And work type is the last categorical group we have, and it has 5 different categories. Since private value outnumbers any of the other categories, we group the rest and we convert it to binary by saying either the work type was private or some other kind of employment. And finally, we have continuous attributes, which are age, BMI, and average glucose level. We convert them to a binary range based on the histogram that we plotted. Here is an example for the age distribution. On the left, we have the age distribution of people who are not susceptible to stroke, that is class label 0. And on the right, we have age distribution of people who are susceptible, that is class label 1. And we see that there is a good spike at the age of 50, and it's also the binary splitting can also depend on domain knowledge. So in general, we know that above 50, the possibility of having a stroke is higher. So based on the histogram and domain knowledge, we chose age below 50 to be one group and age 50 and above to be another. Similarly, for say BMI, a domain knowledge would be that the standard range of BMI for a healthy person goes from 18.5 to 24. So we chose 22 as the splitting point, and a BMI below 22 is one group, and BMI above 22, equal to and above 22 is another group. So for continuous attributes, we turn them into binary by choosing ranges based on histogram and domain knowledge. After we have chosen all the aspects, we feed that into a model that can train based on training data, and that gives us a decision tree. And we use that same tree on a test model, on the test data, and we use that to predict and find results. And that's it for decision tree, and we will move on to Tate Smith, who did K-nearest neighbors.
All right, thank you. So K-nearest neighbors, I think most people in class should know the basics. It's a supervised learning algorithm that can be used for both classification or regression, depending on how you program it. And the basic idea is that similar data points should be likely to have the same Y value or the same label. So in this case, what that means is we can look at this healthcare data and maybe we see that people who are older and who smoke and who have a high BMI, those data points, lots of them should probably be positive for a stroke, and the ones that are younger, less BMI, not non-smokers, those are probably not going to have as many smokers. That's just what we'll expect, and so we can expect KNN to, if we're evaluating someone who does have a high BMI, who is older, we can expect that it will suggest that they're more likely to have a stroke. Just based on looking at all the data points around that data point, and doing, you can either do a vote of those data points. So you can say if more than half of those data points did have a stroke, then we classify this individual as likely, or if they didn't, we can classify it as unlikely. Or you can do a regression to get some, instead of just a classification of likely or unlikely, you can get some score to say maybe how likely they are. We decided to go with the regression. It also changes depending on how many neighbors you use. So we did some experiments looking at up to 200 neighbors to see what value might be the best, as you can see in this chart. What's interesting about this chart is the error gets pretty low right when you get to 25. but we think that's because there's actually a large class imbalance in our data, where most of our rows are actually individuals who did not have strokes. It's less than 10% that did. So we think when it's getting to 25, the algorithm is mostly just guessing non-stroke every time, and that's why it's getting a pretty high accuracy. But when you let it go out to more neighbors and get more data, then it starts to get better. It initially starts to look like it gets worse because it starts actually making more intelligent guesses. But as you let it get more neighbors, it actually gets more intelligent and makes better guesses. So we ended up using around 125 data points. Um, thank you. Yeah, we can go to the next slide. So this is our GUI. We'll do a demo in just a second, but this is just to explain a little bit of how it's designed and how we programmed it. As you can see, it's a window that opens up where you can input a lot of information about a patient. You can click the predict button and that will kick off a KNN algorithm to determine if this patient is more or less likely than the general population to have a stroke. And so now I will share my screen and I'll show you a working demo. All right, are people able to see that?
Yes.
All right. All right, so you can see this is what the application looks like when the user first opens it up. It has no data in any of these columns. So this is just what you can fill out. So I'll start by filling out age. Let's just fill out someone who seems relatively healthy at first. So we'll say 18, female, no hypertension, no heart disease, no, we'll say urban, average glucose. This is just around the average value that we found is around 87. BMI, we'll say 30.2, which I think is a little on the high side. But I think it should still give us a less likely value. Work type, I don't know how much this matters actually. That could be investigated in our future work. Smoking status, we'll say never smoked. Okay, and then I'll explain this advanced section later, but for now, let's just hit predict. And you can see in our results, we have analyzed 43,400 patient records that analyzed it against our whole data set. And the result is this patient is less likely to have a stroke than the general population, which is good because that's what we'd expect for a fairly healthy person, like we specified in the data. So let's change this and let's say it's an older person, 81 years old. Let's say they do have hypertension. Let's say their BMI is 39 something. And let's say they smoke. And now you can see it changed to this patient is more likely to have a stroke than the general population, which is what we would expect. Another part about our GUI, which is an extra feature, is we added this where you can actually specify a different data set that you want to use if you don't want to use the data set that comes with our application. So a data set that we have is train strokes underscore subset. And so all you do for that is you hit load dataset and it uses that new data file. All right, I think that should be all for the application demo. So if we want to go back to the slides.
Can everyone see this?
Yes, if you could go down to the future work, I think that's all we have left. Okay, so for future work, the one thing we thought of is the application could give health advice to the patient based on the information they give. So if it, I mean, obviously it can't, one factor that makes you more likely to have a stroke is you're older. I mean, it can't just tell you to be younger, but maybe it could say to that one factor that's heavily increasing your likelihood of a stroke is the fact that you smoke, and it could heavily advise that you try and quit smoking. Hopefully, there's some more specific advice we could train it to give, especially if we had more data and more attributes, more types of data. Another thing we thought of is it could do some association rule mining, which we didn't have time to do in our project, but it'd be an interesting area to explore. Um, this could find specifically what attributes are most strongly associated with stroke risk. And this could actually give public health officials a way to target specific populations with preventative medicine, preventative health information about how bad smoking is for your health, or how BMI affects your likelihood of a stroke, things like that. And we could also, another area of future work is we could build applications like this for many other illnesses. Any illnesses where lifestyle factors might affect the risk of them, just say heart disease, anything like that. We could see building an application like that in the future. That's all for future work. And that's the end of our presentation. We look forward to questions in class. All right.